You're listening to EE Times On Air, and this is EE Times Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Professor Rodolphe Sepulchre talks about feedback mechanisms in real and artificial neurons. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny is talking about the application of control theory to neuromorphic engineering and vice versa with Professor Rodolphe Sepulchre of the University of Cambridge. After the interview, we will continue the discussion with Professor Ralph Etienne-Cummings from Johns Hopkins University.
Thanks, Giulia. Rodolphe is a control theorist who studied real neurons for nearly a decade before bringing his tools and insights to artificial neural systems. You'll hear about why it can sometimes be easier to make a neuron than simulate one, how spikes can produce both analog and digital behavior in networks, and how Rodolphe has used his techniques for simple robotic control. There are links to his work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. Rodolphe Sepulchre, welcome to Brains and Machines.
Thank you for having me.
Can you start by telling us about your technical background and how you got involved with neuromorphic engineering?
My background is control theory, and after almost 20 years, I got very intrigued by neuroscience and specifically by how neuronal circuits are controlled. Almost 10 years later, a neuroscientist, Terry Sejnowski, told me the work that you do might be relevant for neuromorphic. And I'm very embarrassed to say I had never heard of the word neuromorphic, and that was 2018, so not so long ago. I went to Telluride, and it was an immediate resonance with all the questions that I hear there. And so that was a transition back to engineering. And so most of my work today is in engineering, in control, but inspired by neuromorphic engineering.
Okay, fantastic. Your main contribution over the last few years since you got involved with the field has been to show how control theory can be used to understand spiking systems at multiple scales of size, time, and complexity. Essentially, how collections of neurons can do everything from seeing individual pixels to smoothly moving an arm to planning and executing a project. As I understand it, your analysis begins by separating out the circuitry of the plant, which is a control theory term for the machine that's being controlled, from the controller, which holds the intelligence. Can you talk us through the benefits of this separation, especially for those of us who don't have a control theory background? And then just talk us through step-by-step your analysis.
Great question. Well, the title of your podcast is Brains and Machines. So I would regard a machine as what we call the plant, the system that we want to control, and the brain as the controller, that is the computing intelligence that we equip the machine with. In fact, I think my work sits in between, and I like to think of my work being perhaps relevant for the nervous systems. I hear lots of people nowadays talking about brains very disconnected from any physical machine. And I also hear about people, let's say in robotics or in physical intelligence, wishing to build machines without a brain. And I'm always asking them, but do you conceive a machine without a nervous system? And to me, this is a nice analogy to control design, because control design is really about interfacing what computes and what interacts with the physical world. And it's something that it's not much talked about. We talk a lot about brains, we talk a lot about machines. We don't often talk about the nervous system. But in fact, most of the intelligence of a machine comes from the nervous system, and the brain is just part of that nervous system. Now, going back to your earlier question, which is, what is the role of spike in that interaction? This is something that goes back to my early days working in control theory and designing controllers for machines. I quickly became aware that one of the biggest open questions of the field at the time, but still today, is okay, great when we use the brain and the controller at one scale. So if you use a thermostat to control the temperature of the room, this is a solved problem. But when the control system and the machine spans so many orders of magnitudes, both in the temporal scales and in the spatial scales, and then we are suddenly left with a very different types of machines, and you can go through every concept of control engineering, you see that every concept is struggling the moment you're dealing with a very multi-scale system. Of course, we do control multi-scale system. Think of the power grid. This is a beautiful example of a control system that spans how many thousands of kilometers and very long time span. And so we have come up with architectures that enable this operation over many time scales. But I always felt like there was something very different going on in animal machines. And maybe because of a background in music, I was always struck that rhythm and oscillations were playing almost no role in technology and were looking like playing a huge role in animal machines. And I think this is what brought me to neuroscience. Why are rhythms useful to control machines over many scales?
So there are some really nice results that come out of your work. Perhaps the most satisfying of which, at least for me, is that having the right kind of neural oscillator circuits, so we were talking about rhythms and oscillations, that with the right kind of neural oscillator circuits, analog components can give digital outputs. Can you explain why you're putting these neural oscillator circuits together and how it gets to this digital behavior?
Yes, I think you are using the word oscillators to refer to rhythm or to changes in quantities that are not kept constant, but that keep varying, for instance, periodically. And I think this is an essential role of neuronal circuits to produce those rhythms. And indeed, most of my research before moving to neuroscience was about oscillators. One of my first projects was to build a juggler. And a juggling machine had to start from an oscillator. And I always found it very difficult to design oscillators. I think perhaps the main outcome of working for 10 years closer to neurophysiologists was to understand how neural circuits build oscillators. And they build oscillators in a way that is fascinating because it somehow inherits the reliability that we like in the discrete world, or in the digital technology, and the sort of continuous tuning that we like in the analog or continuous world. So in fact, this is really the core of my interest for neuromorphic is there a way to reconcile the continuous world and the discrete world? And here, I'm not using digital versus analog, because I think this is something different. This is something more fundamental. The dichotomy between the discrete and the continuous that I'm referring to goes way beyond a digital architecture. It could perfectly be implemented in the digital architecture or in an analog architecture or in a mixed architecture. But I think we need to separate the realization question, which is what is the physical architecture that you're going to use, from the conceptual question of where do we put the discrete and where do we put the continuous. And working in neuroscience and working in neuromorphic helped me to realize how much technology has become divided between the analogs and the digital, or between the continuous and the discrete. I grew up in a time where, analog was becoming obsolete and digital was the new thing. And today we are living in sort of the peak of the digital age. But I do think that we have reached a point where there is a lot of reasons why we need to go back to the analog world as well, and to consider that the divide that we have created is also the source of the biggest limitations of current technology. And that has always been my fascination for excitable systems, for spiking systems, that somehow a spiking is both continuous and discrete. It is continuous because it is produced by a physical electrical circuit. But it's also something that is discrete because you can count the spikes. And that is really the core of my interest for spikes and rhythms more generally.
So talk more about how you put these neural oscillators together and the level of complexity that you can get and the complexity of behavior as opposed to the complexity of network that you can get by doing that.
I like perhaps to start from a very, very concrete and simple example, and it is balancing a pendulum. It's the first control lab that any student in engineering has to deal with. And it's also an example of everyday life. I mean, we have all pushed a child on a swing. For me, a neuromorphic way of controlling a pendulum is somehow imitating a child pushing a swing. It doesn't control continuously the velocity of the swing. It just pushes from time to time and knows when to push. And to me, this incarnates the value of neuromorphic in the end. What animals do far better than machines currently do is to control when needed and where needed. This sparsity, this locality in time and in space of the control interaction is really something that could revolutionize control theory and control design if we were able to integrate this intelligence at the core of any device. So when it comes about swinging a pendulum, every control lab, we will use a DC motor. It will have a sensor that measures the velocity or the position of the swing. And this information will be fed back to the DC motor. And the DC motor will try to control or track the trajectory of the pendulum. So this is regulating or controlling a trajectory, a continuous time trajectory. Instead, with this neuromorphic paradigm, we try to go to something closer to what the child does when he pushes a swing, namely to push at the right time. Now, if you want to push at the right time a swing and you want to swing to balance at a certain frequency, you can compute ahead of time how frequently you need to push. So this is where you need your oscillator, your sort of endogenous oscillator that will generate those kicks periodically. And ideally, if you use this oscillator and train the swing, this is called synchrony by entrainment, forcing. Control is more than that, because control also uses feedback. And feedback is very essential to control. So what will be the feedback in that case? Instead of being a sensor that monitors the position of the pendulum continuously, it can be a photodetector that just checks whenever the swing crosses the vertical. And just that event information is fed back to the oscillator and can phase advance or phase lock the oscillator. This sort of interaction between the pendulum and the controller is event-based. It's very different from the continuous interaction that we impose in any machine that we control today.
Okay, and talk about also the positive and negative feedback within the neural systems that you discuss in your papers.
In my early days of getting interested in neuroscience and trying to understand the mechanism that generates those spikes in circuits, at the very start, I discovered the importance of using both negative feedback and positive feedback. As control engineer, we were trained to mostly think of feedback control as negative feedback, because negative feedback is what you use when you need to regulate temperature, let's say, in a room.
So it's all about the error signal, essentially.
It's all about the error signal. But if you want to switch, if you want to make decisions, instead you need positive feedback. So positive feedback is the source of switches. Negative feedback is the source of homeostasis, if you want. And because of the divide that we have created in technology between the continuous and the discrete, nowadays, if we want to switch, it's not control. It's called automation. It's called decision-making. It's a different area. You don't put the emphasis on feedback there. But meeting this mixed feedback architecture from the very start in every single neuron, I learned the origins of my field. And I discovered that if you go back early enough in the days of cybernetics, the mixed feedback amplifier was the central device of electronics, let's say, back at the time. And people were very aware of the advantage of using both positive feedback and negative feedback, depending on whether they wanted to regulate or to automate. So this idea that in one same device you can use both positive and negative feedback, this idea became obsolete after the invention of the computer, because suddenly the computer gave a way to make decisions, to make the discrete switches without a feedback mechanism. And that drastically simplified a lot of machine design, but that also created this big divide between positive feedback and negative feedback. And it's embarrassing to say that I had to be almost 20 years in my career of an academic to realize that somehow mixed feedback was at the root of my field, but somehow had been completely abandoned as a paradigm. And that instead, this paradigm seemed to be central in excitability and the organization of animal circuits.
So talk more about positive and negative feedback within a neural setting.
So what is important is that you can suddenly talk about regulation and automation in the same language, in the same circuit. And you can identify it in the architecture of one circuit, the source of positive feedback and the source of negative feedback. In the same way as in the early days of the mixed feedback amplifier, you would use the same electronic device, the op-amp, and would use one wire to connect to the positive feedback entry and one different wire. So you have this built in the architecture, and you know exactly that if you push more emphasis on one wire than the other, you can tune the balance between the two. Having both in the same device creates unique possibilities if you want to somehow reconcile automation and regulation. If you look at the animal world, it's impossible to say, this is automation, this is regulation, this is decision-making, this is homeostasis. It's always mixed at every level, from the single neuron all the way to the behavior. And I think there is something very essential behind this simple observation in explaining why animals are so better at doing tasks that somehow intertwine the discrete and the continuous.
Okay, so let me try and take an example that I think you gave in one of the papers, which is that we can think of the input coming in from sensors, for instance, as the excitation, and then we can think of the refractory period and what's happening during the refractory period as the regulation. So you've got these two things that are going on in a neuron. And then if you wire these things together in such a way that they're inhibiting and exciting each other, then you can get these interesting behaviors. So you built a snake model.
Yeah.
Can you talk about how that combination of inhibition and excitation worked to make this snake slither across?
Yeah.
Well, I think it was a simulated snake, but...
Absolutely. It's being built at the moment, but you are right that currently what's in the paper is a simulation. Now, I think of this snake just as a scale version of the pendulum example that I discussed earlier. You have 4 segments or 5 segments, and what we control are the joints. So you control the relative angle between the segments, and you want to orchestrate this muscle activation for the snake to move. Okay? It's a cartoon, of course, but a snake is more complicated than that, but it's already more complex than the pendulum. Now, anyone who builds a snake will make a distinction between the low-level control, which is just the muscle activation, and the high-level control, which is, deciding whether I should turn left or right. The latter, we call it decision-making. The former, we call it regulation or homeostasis. So we create very often this separation. This creates all sorts of difficulties when you build a snake, because you have somehow to reconcile these two conflicting languages, the one discrete language of automata and the one continuous language of differential equations. And I shouldn't say we have created a snake, we have created a nervous system for the snake. This nervous system of the snake has this feature that somehow mixes the continuous and the discrete in the neuromorphic language at every scale. When we talk about muscle activation, it's very much like in my pendulum. I need to decide when to activate the muscle, and I need to activate the muscle at the right time with the right amount of let's say, strength. That's the continuous problem. But then I want the snake to move. So now I need to orchestrate 4 controllers, not just one. And now I see that I need to organize these moments of actuation. I need to organize them in a sequence. And it is a sequence that will lead to the motion. This is usually solved in the discrete world. And so I could continue like that. But in the end, the nervous system of our snake is made of 100 neurons that are all the same, all have the same architecture, and that all have this mixed feedback structure. So that whether I look at the snake at the muscle activation level or at the behavioral level, I can always address the design of the discrete and the design of the continuous. What does that mean? Let me go back to orchestrating the sequence of motion so that the snake moves. One thing is to orchestrate the sequence. I don't want the 4th segment to move before the 3rd segment because I want to create a wave. But at the same time, the sequencing is not enough for the snake to move. It needs to move with the right phase lag. And that phase lag is very physical. So that phase lag depends on the uncertainty of the environment. It's not something that I can decide in hard stone. It's something that I need to adapt continuously. So you end up thinking of the nervous system as an orchestron. And it's an orchestron where you need, on the one hand, to orchestrate sequences. It's sort of the music partition. But then you also need to tune the pitch. And this is very continuous. And doing both in the same design framework is something that I think is opened up in a very novel way using this mixed feedback architecture.
I don't want to push this too much further because it gets very mathematical. But people who have been listening to the podcast will have heard us talk about central pattern generators before. Yep. And I know you reference in your papers people like Auki Eisbert from APFL. So we know these generators, we know these oscillators work for these kind of control problems. Why don't you focus on what it is that you're adding in terms of value there?
Right. Well, it is precisely the fact that either people think of the design of those machines as central pattern generators. And usually those people like Auki Eisbert start from the continuous world. They start from the physical world and they take bio-inspiration to imitate neural circuits to orchestrate those rhythms. But then at some point you also need to make the supervisory control of the snake. When does the snake turns left or turns right? What happens if it bumps against the wall? And this is where usually people switch to a different language that will come from decision-making, from computer science, from the discrete world. And then they struggle to somehow make those 2 levels of control interacting with each other. That's why if you go today to a control conference, you will see entire tracks devoted to that question. People call this cyber-physical system. Cyber-physical systems are made on one hand, a big computer that works in a discrete fashion. On the other hand, a big physical system like the power grid that behaves in a continuous model. And they struggle to interface at every level of the control design.
So what you're showing is that there's no reason that you would have to move to a conventional algorithmic digital substrate in order to do those higher levels of thought or of planning or of decision making. But as far as I can tell, what it doesn't tell you is how exactly to do that.
Okay, yes. And I want to explain that without going into technical details. But what we have seen in the last 2 decades, because of course everyone is aware of this big question. It is the big question of the field, how to reconcile automation and regulation. The dominant trend is to develop a new framework that I regard as the union of the continuous world and the discrete world. And this is called the framework of hybrid systems. So hybrid systems allow you to either consider differential equation or to consider discrete logics in the same package. Okay, this is great, but this has limitations. And the main limitation comes from the fact that it makes the design framework very complicated, because already the design framework of ODEs alone is difficult. The way I regard neuromorphic system is instead a very, very narrow class of differential equation that have the property that they can also be regarded as a discrete event system. And so I like to think of neuromorphic sitting at the intersection of the continuous world and the discrete world, rather than at the union of those two worlds. And for me, intersection is always a tremendous source of tractability. How is this illustrated? If you want a concrete example, in the snake, we use two paradigms in our architecture, and the two paradigms are very well known separately from each other. One is winner-take-all, and I don't need to explain it, but it's very well known from computer science. It's a discrete paradigm. The other is the rebound excitability, which is a very well-known paradigm that is studied in electrophysiology. To the best of our knowledge, no one has ever considered an architecture that mixes these two paradigms and that creates a network where the nodes rely on the rebound excitability and the network relies on the winner-take-all architecture. So I find this fascinating that we can take some very well-known paradigms, but that the neuromorphic architecture gives us a way to connect these two paradigms where conventional methods struggle.
Another thing you mention in your papers, and you cite a Turing paper for this, is you talk a little bit about morphogenesis. And for anyone who's read any complexity theory, morphogenesis is what gives you these beautiful, complicated patterns in natural objects such as leaves and animal skins and shells and this kind of thing. So essentially what you're pointing at is the fact that we get these incredibly complex behaviors, visible behaviors, if you like, out of very simple elements and physical, chemical interactions. Is there some way that we can neatly extend that metaphor to intelligence?
Yes, you're now bringing me to a sort of the philosophical nature of the question, because this divide between the discrete and the continuous that sits at the core of my research is a philosophical question that goes back more than 3,000 years. It has always been a sort of a mystery across time, across civilization, across disciplines, to understand how the discrete emerges from the continuous and how the continuous emerges from the discrete. And I think this is the central problem of morphogenesis. How do you get 5 fingers from initially chemical that are just mixed in the continuum? How does the cell suddenly acquire a shape of discrete nature? And so this is, to me, explained by the mixed feedback mechanism, or rather the mixed feedback mechanism is central to that. So once again, I'm sort of obsessed by the mixed feedback mechanism because I do think it has an enormous potential in contributing to that fundamental question of how do you get the discrete emerging reliably from the continuous, and how do you get the continuous to emerge reliably from the discrete? And so I'm hoping that we can sort of pile up the scales in this way, and that the discreteness of the small scale becomes the continuous of the next scale, and then itself becomes discrete. And so this is how you go from the cellular scale all the way to behavior. Of course, we are not there yet.
Okay, so we've got the beginnings, at least, of a framework that can answer questions about neuromorphic systems. We've talked a lot on the podcast about theory being desperately needed in this field. So how is that going to work? How is it going to grow in terms of demonstrating the kind of design rules that you would have for having multi-scales of neuron clusters or oscillators or bunches that are working together, working on different things, passing information back and forth? And how far are we along that road? So it sounds like quite a long road to get to a really comprehensive theory. How far are we along it, and what needs to be done to get further?
This is a question that I struggled with 10 years ago when I was working close to neurophysiologists. The questions were fascinating to me. The answers were very, very puzzling to me. When I started working in neuroscience, I got the first paper rejected ever in my career. And for the next 5 years, most of my papers were rejected one after the other. I'm very grateful to all the reviewers who rejected my papers. Because during those 5 years, I learned an enormous amount of information that I don't know how I would have learned otherwise. I still believe in the scientific community, in the role of peer reviewing, in the role of interactions between people who don't really understand each other, but who believe that there is value in making an effort to understand each other. Neuromorphic is a great community also in that regard. It is a community where I have encountered a lot of openness to novel ideas, to different ways of thinking, even if they are very much at odds with the conventional ideas. And this is why I'm so grateful to Terry Sejnowski to have brought me to Telluride, because I'm now back home. I'm an engineer at heart. And I really believe in Feynman's viewpoint that what I cannot build, I do not understand. I do think that building machines that demonstrate this mixture between the continuous and the discrete is at least my way, my angle of attack. And so the price that I'm paying for this, it's a very slow program. I spent nearly 10 years trying to understand and to better understand how a single neuron works. And many people were laughing at this. So how can you possibly say anything valuable for the brain if you spend your life studying the neuron? Okay, maybe it's an attitude, maybe it's a sort of a bottom-up choice and others prefer the top-down choice, and I think we need both. But I'm quite fascinated by how efficient the bottom-up approach is now, and that somehow we spent a lot of time, perhaps too much time, on the single neuron, but we identified key mechanisms that now are very easy to scale up. And going from the single neuron to controlling a pendulum was an easy game. Going from the pendulum to the snake was even easier. And I do think that going from the snake to a next nervous system that will have 100,000 neurons instead of 100 neurons will be even easier. But of course, we need to develop methodology and theory to do that. And this is what, for a long time, I wondered, what would be information theory of events? Do we need to start from scratch? It doesn't look like intelligence to have to start from scratch. And I think this is where this idea of working at the intersection came up. Because what I see now when we design the snakes is that we can borrow existing paradigm from both the discrete theory and the continuous theory, and we have the way to mix them. So that I find very encouraging, the fact that perhaps we won't need to develop that much new theory, but we will need to acknowledge the role of excitability. And for most people building machines today, excitability is an epiphenomenon.
Okay, let's move on. You were talking about spending a long time on one single neuron. So I want to ask you about the Hodgkin-Huxley neuron. Hopefully by now your paper has come out, your editorial about the Hodgkin-Huxley neuron and how it is so much easier to build than it is to simulate. And it has all these nice complex behaviors that if you can just build them and put them together, you can do a lot of stuff. Can you talk a bit about that and how you were inspired to write that piece?
First of all, I came across the paper of Hodgkin and Huxley in the second year of my PhD, almost 20 years before I started doing research in neuroscience. And it was a complete accident. I entered a room where there was a reading club and they happened to read Hodgkin-Huxley paper. And it was an immediate flash. You fall in love with someone, you don't know why, but I never recovered from reading this paper. And immediately I felt like this must be one of the most important scientific papers of the 20th century. I still believe so. And not many people think that way because, as I said earlier, the role of excitability has sort of gone down in artificial intelligence and so on. Okay, now, when I started doing research on Hodgkin-Huxley, I started from the differential equation. And I went to read books on neurodynamics, and I found them very difficult, full of bifurcation theory and whatnot. And somehow I felt like it was very much at odds with what a neuron should be doing. For instance, I got very much hooked in neuroscience in the topic of neuromodulation, which is the fact that these chemicals, these peptides, these neuromodulators constantly reshape the rhythm and modulate the rhythm in a fascinating way that I found was never addressed in the books of neurodynamics. Because neurodynamics tends to describe the behavior of a neuron as a dynamical system that you would use to describe the motion of planets. meaning that it's a very isolated framework, but a neuron never behaves in an isolated environment. It keeps interacting. So to cut a long story short, because I spent almost 10 years trying to figure out, the outcome is, again, very embarrassing, but I went back to the first figure of Hopkins-Huxley paper, which is not a set of differential equations, which instead is an electrical circuit. And this had really been the work of the last 5 years or so, going back to engineering and having to build those machines rather than simulate them, the importance of the circuit architecture. And the fact that this amazing mixed feedback property of Hopkins-Huxley model doesn't come from the specific form of the differential equation. It only comes from the constraints that are built in the circuit architecture. And the fact that the moment you build any machine that incorporates that same architecture, you will have the same properties. And it's not at all about replicating the same differential equation. It is about acknowledging the constraints. And this is something that has been perhaps the most important lesson of my career, because I work in a field where mathematics today has become the dominant language. Most people describe models in terms of differential equations. And I have nothing against mathematics. I love mathematics, but somehow I think it's something that we will need to go back to acknowledging the architecture of a simple electrical circuit, something that most people find obsolete today.
Very good. Before we finish, I want to put you on the spot and ask you how you see neuromorphic engineering evolving over the next 10 years and how your contributions might push it in one direction or another.
Okay, I think those are two different questions, and perhaps I would prefer to answer to the second one. I'm trying to push neuromorphic in a different direction that it currently moves to. Today, there is a lot of emphasis on neuromorphic computing and on emulating what digital computers do well with neuromorphic architecture. I cannot make any predictions about that because my focus is elsewhere. Instead, I'm focusing on what computers don't do well. And to me, this is where there is a tremendous potential for neuromorphic. And I will just speak for my field, for control. I see that there is a tremendous potential in developing methodologies that enable the design of machines that interact when needed, where needed. And if we can achieve a tenth of that, we will make a huge impact in energy efficiency, in making technology greener, more diverse, more human compatible, I would say. And so, yes, I do think that there is an enormous potential and that we are only at the start of possibly a sort of paradigm shift that I think we all feel is needed today.
Rodolphe Sepulchre, thank you so much for coming on to Brains and Machines.
Thank you very much for having me on the podcast.
Thank you, Sunny. So this interview has been a jump into a million questions. And for more about Rodolphe Sepulchre's work, please go to brainsandmachines.net. And now we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hi, Giulia. Hi, Sunny. Nice to see you again.
Hey, Ralph.
Ciao, guys. Ciao, Ralph. So this interview was really interesting. And Rodolphe makes a striking observation, right? He refers to our podcast, Brains and Machines. And he says that people often talk about brains and machines separately, but rarely they talk about the nervous system, which is actually connecting the two. Do you agree?
No, because I think if you look at the very essence of neuromorphic engineering, that's exactly what we've been doing for the past, 30 years, since the mid-90s. But I think what he was referring to, though, is something slightly different. He's talking about the interaction of machines with the environment and then the computation that happens independently. And if I remember correctly, he was basically saying, look, at the end of the day, we need to basically combine these two things together, the interaction with the world and the intelligence. And that's when he talks about all these different machines that he's implemented, like the snake and so on and so forth. That's the impression that I got. Not so much that folks have not been thinking about this.
Yeah, I also agree with Ralph. The nervous system has been critical to my understanding of what neuromorphic engineering is from the beginning, from the things that we talk about all the time, like Mark Tilden's work, from some of Ralph's early work with robots that I remember from back in the day, where it was the spinal cord stuff that you were doing with Vivian Michaud back when she was in Alberta. And Tony Lewis.
I mean, Tony has been working on this from his thesis.
Yeah, so
PhD
I think
thesis.
that concept of nervous systems has been right there in neuromorphic for as long as I've been around it, which has been a long time. But I think that idea of the embodiment and bringing the movement and the control, making it more local, is a critical issue, and he is really right to highlight that.
So I took this as a point of discussion indeed, because my boss is Matej Hoffman. He has done the PhD with Rodolphe. That's why I started embodiment, and I started to look at embodiment for my Marie Curie postdoc, and I came here in Prague to work with him. So the point is that this is a kind of like a provocative question for you two guys. Lots of people are talking about embodiment here and there. Same thing also for active vision, but there's not really so many taking into consideration the real interaction with the world, so the real shape of the body because of what happened outside and vice versa, and the distribution of the sensors that matters, and all of these things that play a crucial role for the algorithm itself. So my provocative question is, if you can give me some sort of a percentage of how many people say that they do embodiment and how many people they really do.
Yeah, look, I mean, I think absolutely, right? I mean, especially given the fact that, you think about what, your previous lab as well, right? In Genoa with Chiara and so on, right? Embodiment has been an important aspect of all that work. There's no question that embodiment is important to understand how brains actually develop, right? There's this classical example that I've heard like here and there about this animal that basically grows a brain while it's moving around, and then when it stops moving, it eats its own brain and goes into stasis. Basically, it doesn't need a brain anymore if it's not exploring, right? If it's not interacting with the environment. And I was arguing that ultimately we cannot not look at development of brains with exploration, with the embodiment part. Those two things have to work together. It gives us much better ability to understand how to control how the brain works, essentially.
I think the issue of control theory is critical to it. There was an interesting LinkedIn post I saw just before Christmas where someone was posting about some robot that was being controlled using LLMs. And they were complaining about one aspect of it, like it was quite brittle because it didn't know what to do in lots of circumstances. And my attitude was, yeah, and where is its brain? I guarantee you its brain is nowhere near its body, which is introducing all sorts of issues. If you want the brain and the body to be together and to be powered by something sensible and local, then you're going to have to do something like neuromorphic engineering.
There was also an interesting set of robots on the web where you see these really elegant walking robots, right? I think it's from China. And the idea was there that, oh, look, we are able to make these machines walk a lot more human-like, as opposed to this weird tentative stepping that you see in the classical set of walking robots that we've seen so far. But I would argue that if you go back and you look at some of the work that Tony Lewis did with some of the walking machines that we did, because it was built on actual neuromorphics with neurons and spikes and all the machinery of neuromorphics and the sensing and so on, and we were also using algorithms that are more similar to what you will find in the nervous system, in the spinal cord, we were able to get those same elegant walking. Now, we didn't have the balance and all that stuff, right? So I don't think to be even remotely similar in that sense. But in terms of the elegance of the walk, there's no question that we were getting that way before these robots were doing it.
But I think the importance of Rodolphe's work was that he was pointing at a way to tease out the theory, behind how we can separate the brain from the body or the brain from the nervous system, the sort of automatic from the learned aspects of movement. And that was what I found particularly interesting as I was reading through his stuff in preparation for the interview.
Sure. I mean, the whole oscillations and discrete and continuous interplay, I think, was really interesting. It's something that folks have been looking at for a while. And the controls that he talks about in terms of when do you turn on certain controllers, when do you turn it off, when do you get inputs and outputs from the world. It reminds me a lot of Steve DeWerth's work with his whole entire replication of a Leach circuits for locomotion, where everything was interacting. There was up signal, down signals, side signals that were basically trying to represent all these different control paradigms. Now, I don't think Steve had quite looked at it in that theoretical detail that Rodolphe has, but on the other hand, it's another really cool example of seeing that embodiment and try to provide ideas about what the nervous system might be doing. Another component that I thought was particularly interesting was his statement about the Hopkins-Huxley neuron and the fact that he looked at it and it was a circuit and he was like, well, you're going to really see what it can do is to build it. Then that again reminds me of Misha's work, right? I mean, that was, Cover of Nature, the first full neuron implementation in hardware, tried to implement all these different components of the Hopkins-Huxley. And then, of course, a number of folks afterwards have tried to capture it in different ways to try to make it more efficient and so on. But all of those are natural flow that comes out of what Rodolphe has talked about. The one last point I want to make is this. He said something that kind of struck a little note with me, and that was basically saying, at the end of the day, we shouldn't be trying to make neuromorphics do what regular computers do. He talked about what is that they can't do. And that's really the thing that we try to do. And I could not agree with him more. And that's particularly why I also think that the whole push to benchmark may be a little bit misguided. Although I know we all want to be able to compare our systems, but it's hard to benchmark when you're talking about things that computers can't do.
Yeah, another thing that I'd like to say is that me and a bunch of people with the lead of Elisa Donati will come out with a paper talking about embodiment and benchmark for embodiment agents. And I got quote from your comment, Sunny, saying that if you want to do embodiment, then neuromorphic could be a way. And I have my response, but I'd like to hear your response. So from our point of view, of course, neuromorphic does no doubt handles better different timescales, but I'd like to hear your thoughts.
For me, it's all about power. It's all about power, and it's all about tying together different systems that talk in different languages. Spikes are a really nice language because it's not just one, it's lots of languages. And so you can use a rate code if that is the most efficient way of communicating one kind of information. You can use a time-based code if that's the best way of communicating a certain kind of information. And you can switch between them. It's almost like phonemes. It's like you can use phonemes in one language or another language. You don't have to choose. And I think that's one of the things that's really elegant is you're not having to say, okay, this is going to be purely analog. This is going to be purely digital. And actually, this comes out in the interview with Rodolphe. You can use pulses or spikes to be analog and to be digital or somewhere in between. And we know that there are parts of the brain that are kind of neither analog nor digital. They're a fuzzy mixture between the two. And that's elegant. It means that all of these different systems, which are working with different signals, which are working with different time constants, they can do whatever is best for them, but then still have a common language with which they can exchange information. So that to me is why it's critical for embodiment.
I like another angle that you brought in as well, which is something that I've been talking about over the last few podcasts, which is this notion of the sparsity shell. And that's exactly what he referred to, that time dynamic, if you will, between the spikes and how the action that needs to be taken and the compute that needs to happen in order to lead to the action, that happens on varying timescales, creating this distributed, if you will, sparse representation. So again, we come back to that same thing, whether or not it's intentional, but it's part of the way the world operates, if you will.
So because I'm the producer of the podcast as well as doing the interviews, I listen to it over and over. And I was listening to the discussion where you were talking about the sparsity shell.
Mm-hmm.
And as much as I love Chris Tumazu's analog shell concept, I actually think that the sparsity shell is more on the nose. It does pinpoint much more clearly what's going on and why it's so important. And it does happen to coincide with being the analog shell, but it's about that idea that where are you going to throw away information and what information are you going to throw away and how are you going to make that decision? And that decision can be based on learning and it can be based on temporally local conditions. You could be, I'm going to throw this away right now, but I'm not going to throw it away in 2 seconds' time because things have changed or things are being modulated, maybe in a periodic fashion. I think it's a very deep concept. So I'm glad you're pushing it, Ralph. And I think you should continue to do so. The sparsity shell is really important.
Yeah. Another thing that I'd like to mention is sensory motor contingencies, which is a thing that is very linked to embodiment. So this relationship between the sensory input and the action that you perform, right? So then at the end, you will have a sequence in time that tells you what happened in terms of interaction with the environment. And that is really important. And all of this theory come from Kevin O'Regan and lots of other great people. But now I want to ask you another thing that I found interesting because he emphasizes that building circular architectures, it's better rather than simulating differential equation. And I want to know your point of view because I might get his point, but still we need to speak to a broader audience and we need to be understandable for everyone. And having this simulator is really important.
Yeah, I mean, from my perspective, it was always about how do you really represent the real world with all its variabilities, with all its nuances, with the noise and the changes, the unexpected input that comes in and so on and so forth. That was always why building it provided you a better way to see what happens, right? So that's why I like building things better than just simulating it. But in the ideal world, if you could represent everything, then simulation would work as well. But we can't. That's my perspective.
But I would add there that the problem is always that if you choose to try to represent everything, then you are counting on yourself to get it right.
And it gets big.
Yeah. Which is why we talked to Barbara Webb a few months ago and why she and a whole cohort of roboticists use robots rather than simulations to try and demonstrate their neural principles because they want to see if these things work in real life and are robust enough to work in real life, even though it's a slightly different real life than you would have in an insect, in her case, that with all of the friction and the different kinds of noise, right? Because a lot of experiments, they'll throw in some Gaussian noise and all of a sudden, magically, it's supposed to be a real world simulation. And I think, let's be honest, the world isn't quite so simple.
Yeah.
So
cannot write it with one simple bell curve. It's a little bit more distributed and random and variable than that.
Yeah, I mean, don't get me wrong. I usually do everything on the robot. Actually, like I try to do active vision, which is a nightmare. I can't go on simulation. So I totally agree. But still, just from the neuromorphic community point of view, it's good to talk to everyone and it's good to give tools to everyone to just get interested and then at some point move to the robot point of view. If it doesn't work on a robot, it does not work. And this is a motto, like a slogan that I have, and I will continue to say it for the rest of my life. So I totally agree. Another thing that I found interesting is that at some point he was talking about the fact that analog became obsolete and then there was the peak for the digital age. And then he was saying that maybe neuromorphic is leading a renaissance of analog of mixed signal, which is a thing that reminded me of Charlotte Frankel, that she's going again back to analog. So this is a nice crossover that I think it might be interesting to say.
I have one reaction to that.
Yeah.
And it's might be controversial to what you're saying. I don't think analog ever went away. I think it was different, right? I mean, everything that we have in terms of our music, in terms of our sound systems, everything is analog, right? So it was just not used in the same way, right? Maybe in computation, digital computation was primarily the way to go. But now analog computation is becoming more important again. So maybe that's where that loop becomes relevant. But analog never went away.
I suspect the real problem is not about analog going away or coming back or whatever. It's really the fact that analog is more difficult, right? It's mathematically more difficult. You can't just sit down and hack it the way you can with Python or, it's not so simple. And we are not training as many analog engineers as we used to. People are not choosing to do as much analog as they used to. Maybe, Ralph, you have something to say about that. Are you getting enough people?
No, I'm teaching a course, sophomores, first layers of analog and applications and so on. And my class is oversubscribed. So maybe there's more interest again. Maybe he's coming back. Maybe I'm agreeing with him. Julia, maybe he's right. Maybe it is coming back in some way. That folks are caring enough again about it and so on.
It's hard to tell. I think I did, but this was 20 years ago. I looked into the trajectory of teaching of analog electronics and how it had changed over the years. And it could be that, it went down and it's coming back again. But I'll see if I can find something to put into the show notes, see if somebody's actually done that study. And if I can find something, it will no doubt be the topic of discussion in one of our future episodes.
So let's stop it here. Thank you, Sunny, for yet another great interview, and Ralph for your invaluable comments. In our next episode, Sunny will be talking to Sally Ward-Foxton, who covers AI for EE Times. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Professor Rodolphe Sepulchre. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript along with direct links to the other stories we've mentioned and other resources. Thanks for listening.